Right. The things to write.
And then a little bullseye.
No, I'm leaving the recursors are out today.
When you do a family picture, is that how it is also with like your kids?
I think the one I'm pissed off at the most goes right in the middle. Bullseye. Yeah, we should do family pictures like that. Okay, we're going to talk more about undecidability and reductions, showing that other problems are really hard if these problems are hard. So yesterday we spent a long time, and we've done it many times, so I'm not going to go over it anymore. So in your heads you should know that this problem, where you're given a Turing machine and you're given an input, and you're trying to know whether that Turing machine accepts that input and stops and says yes, that problem is undecidable. You can't make another Turing machine that goes ahead and accepts these things. There's no way to do it. And this problem sits over here in undecidable land, recursively enumerable land. It's undecidable, but you can at least decide it halfway, in the sense that if somebody gives you a machine and an input, and it does actually accept that input, you could answer yes consistently and get it right every single time. It's just that if it didn't accept the input, you would never know it, and you wouldn't be able to answer no correctly. So because of that, if I took the complement of this, the pairs mx where m doesn't accept x, and I wanted to accept only pairs like that, there would be nothing that would consistently say yes correctly to that. There's no way to know if the machine doesn't accept x. And that machine, the complement of this, would sit in here. So if we call this, I think the book calls this, what is it called, ATM? It's got some name for this. Anybody read the book? Acceptance of Turing machine. I think they call this ATM, or just where you get your money. And here's ATM, and here's the complement of ATM. And this is very, very typical, that an undecidable problem has a complement that's not even partially decidable, that you can't do at all, that's not even recursively enumerable. It's possible that both a problem and its complement lay out here, but it's impossible that both of them would lie in here, because if they were both recursively enumerable, then the problems would both be recursive. You could answer yes and no, and they would go collapse even further down into the decidable realm. All right, so what we're going to do today is show that there are other problems, natural problems to ask about Turing machines that are also undecidable, and then we're going to shift out and talk about complexity theory for the last 3 or 4 days. Good morning. All right, so here's a problem. We're going to work this through together. Here's a problem. We'll call it empty TM, ETM. Somebody gives you a Turing machine, and I want to know if that Turing machine accepts absolutely nothing. Okay, it accepts the empty set. That means there's nothing at all in this Turing machine that will ever get accepted. We're wondering, maybe there's a way to do this. After all, there is a way to do this if this is a context-free language. If I give you a context-free language, a grammar, and I say, does it accept absolutely nothing, there's a way to do that, because you check the start symbol and see if it's useful or useless. So there is a way to answer this question for context-free languages. Hopefully, now that we've risen up a level, we can still answer the question. But unfortunately, we're not going to be able to. It's going to be undecidable, just like this is undecidable. And the way to show that these kind of problems are undecidable is to reduce this starting out problem that came from diagonalization to these new problems. And the reductions are all really similar. And basically, after we do 2 of these examples, I'm going to just tell you this general theorem called Rice's theorem. And the theorem basically says that anything interesting that you want to know about a Turing machine is undecidable. Okay, that's intuitively what the theorem said. All right. So let's think about this. How do we reduce this problem to this problem? Without getting into a gory definition of what reduction really means, here's the idea. I want to convince you that if you could solve this problem, then you could also solve this problem. And since we know this problem is not decidable, that would imply that this problem is also not decidable. So I need to show you a conditional idea that if you could solve this, that if you guys went home and told me you had a solution for this, I could use your solution and solve this thing here that I know is impossible. And that would imply, therefore, that you are lying to me. You don't really have a solution for this. Because if you did, I'd solve a whole bunch of impossible things. So how can I use your hypothetical solution for this to solve this problem? So now think of it from my point of view. I want to solve this problem. And I've heard through the grapevine that you have an algorithm that takes a Turing machine and tells me if it accepts absolutely nothing. I know that exists somewhere, or I think it does. And I'm trying to solve the impossible here. I'm trying to decide whether M accepts X if somebody gives me a machine and an input. How can I solve this problem if I have somebody who can solve this problem? That's what I want to think about. And it's tricky only because it's kind of a meta way of thinking. Questions about Turing machines asking questions about other Turing machines, and complex connections. But when you actually come down to the logic, it isn't going to be so hard to do. So I want to discover it together. I want to try ideas that won't work, and then I'll show you an idea that does work. So if I just show you the idea right away, you'll mechanically see how it works, but I'm not sure it'll be so I don't know, so much of an epiphany. So let's at least imagine now that there's a way to do this. You know, if I give you a machine, you can stare at it for a while and tell me, hey, this doesn't accept anything. Or, oh, this accepts something, I can tell. You've got a way to do that. How are you going to solve this problem? So somebody gives you now a machine and an empty string. You've got to figure out whether a machine and a given string. You've got to figure out whether the machine accepts that string. All you have at your disposal is your own logic, and this is a subroutine. What can we try to do? Let's try something that might not work, but at least try something. Okay, we've got M, we've got X, and I got this as a subroutine. I want to know if M accepts X. What if I try this? Just a brute force approach. I'll go ahead and I'll send M to you guys. You've got this empty checker. And I'll say, hey, does M accept absolutely nothing? And you're going to give me an answer, yes or no. Now what if you tell me, yes, it accepts absolutely nothing? Then can I answer my original question? I can. I'll say, no, it doesn't accept X because you just told me it accepts nothing. Everyone agree? Well, I'm halfway there. If the other side works now, if the no side works, then I'm all done. And it's trivial. All I got to do is pass it over to you. So now I pass it over to you, but this time you say, oh, it accepts something. And then I go back and say, oh, well, now I don't know how to answer the question. I don't know if it accepts X or not. I know it accepts something, but maybe it accepts something else and not X. Maybe it does accept. I've learned nothing. So if I give it to you just brute force without thinking about doing anything to this M before I give it to you, I don't get a helpful answer unless you give me a particular answer that I like. But if you give me the other answer, I don't learn anything. All right, questions so far? So I got to fix this. I got to take this machine that somebody gave me to determine whether it accepts X or not, and I have to play with it a little bit, change it in a very particular way that I have control over, and then give it to you. And I have to do this in exactly this possible way. I've got to do it in such a way so that when you tell me the machine accepts nothing, I know that this M doesn't accept X, just like before. But when you tell me that it does accept something, then I know that this machine accepts this X precisely. But if I just give it to you straight, it doesn't help. So I have to fiddle with this M first. I got to play with it. I got to manipulate it so that when you say it accepts something, it actually does accept X. So do we have any ideas of how we can fiddle with this machine? It's going to seem just like a trick, like magic when we do it, because it's not so complicated. So, but you're allowed to fiddle with this machine. You can do anything you want to it. So what should we do? So here's what it's going to look like. Hold on. So I'm given MX. I'm going to change it to something else. That's going to be just a single machine. And that machine goes over to you. You give me an answer. I take the answer. I send the answer back to the original question. This part is called the reduction. The part that changes the input to my original question into the input to your question. Okay? That's the way to think of it. So how should I change this machine instead of just doing this? This doesn't work. Just copying the machine over doesn't work.
Can you tack something on the front of the machine that you know accepts X, so that only X could get through the machine?
Sure. Sure, I can try to do that. So what should I do precisely? You're saying I should take this algorithm. Think of this as a program. If you don't like Turing machines because it confuses your way of thinking, just think of M as a program. Somebody gives you a program, and they give you an input to your program. So Michael's suggesting that the first line of my program, I check for I change the machine to check for x, and if it's x, I just say yes.
No, if it's X, you keep going.
If it's x, I run the machine.
Right. And if it's not X,
And if it's not x, what do? I just
you reject.
reject. I could certainly throw that if statement in. I could throw it in right at the beginning of the program. If the input to this program is x, then run the program. Then continue with whatever was there before. Otherwise, skip the whole program, go to the end, and say print no. Does everyone understand Michael's suggestion? Now, he's obviously got some idea of why he wants to do this, but let's check if it helps us at all. So we'll call this new machine M for Michael's machine. And let's remind everybody what this machine is relative to capital M. This machine is the same machine as capital M except for the following addition. It has an if statement at the top that says, if the input to me is equal to the string x, then actually continue in the program. Otherwise, skip to the bottom and print reject. It's different than this machine. This machine actually goes ahead and runs itself on any input you give it. This machine does exactly what this machine does, but only if it's given the input x. Otherwise, it always says no. So this machine is going to do what? What's the possible acceptances that this machine might do?
XX.
Well, either it's going to accept x, or if you give it anything except x, it's just going to reject. It's going to accept nothing. So we don't know exactly which one this is going to do. It might not accept anything. It might not accept x either. But if it's going to accept anything, the only thing it has a chance to accept is x, because that's what it does at the first line. It says, if the input's x, then go ahead and run the machine. Otherwise, skip to the end and reject. So the only possible languages for M sub little m are the empty set and the single string x itself. So it seems like it's a good idea, because at least that puts us in the realm of the empty set still tells us that the answer is no to this question. But if it's not the empty set, the only possible thing that could possibly be here is just a single string. So we get the answer from this empty question to the question of whether m accepts x. Here's what it looks like. If the input equals x, then run m as usual. Else, print reject. That's what MM does. So if I want to figure out, somebody gives me a machine and an input string. I want to figure out if this machine accepts this input string. Here's what I do. I take the machine, I put in this if statement at the beginning, and I give it to you guys, and I ask you, does this machine accept something, or does it accept absolutely nothing? That's my strategy. Right, so let's go through the possibilities. I give this machine to you, and you tell me that this machine accepts something. So what is this machine possibly going to be accepting? This machine rejects everything except possibly the input x. That's the only thing it ever runs on. So if you tell me the machine accepts something, what's the only thing it could be accepting? X. So if you say the machine is not empty, that it accepts something, then I know for sure that my original machine accepts x, because if this machine accepts something, the only thing it could accept was x. And when it accepts x, it's running m on the x. So I know that m accepts x. But if you tell me that this machine I give you, this m sub m, is empty, that means it rejects everything. It already rejects everything except x, but if it rejects everything completely, then it's also rejecting the input x, which means that the answer to this question is no. That part worked before. But the part that works right now is the part that when it accepts something, it's got to accept x. And the trick is just focusing on the input that's x.
It really does seem like a trick.
It's a trick.
It doesn't quite seem kosher.
It is kosher, but it's a trick. It's a kosher trick.
I mean, it's easy to make a finite state machine at the beginning of your Turing machine that just runs through x and goes to a dead state.
Yeah, well, I don't know. I mean, you shouldn't really doubt that I can do this. I could do this. You give me a program, I'll go in there in my Emacs and type in, if the input is x, because I'm given the m, I'm given the x, I copy the machine over. I copy the x over to this if statement, and I say if input is x, then continue and run the program on x. Otherwise, just go to the end and say reject. It's a trick because this problem is really no easier than this. This is just darn hard. And if you can do it, you can do anything. OK, so here's the big picture one more time. Somebody gives me m and x. I convert it by a reduction to this new machine. Here's the new machine. And here's the truth. The new machine, mm, accepts the empty set if and only if m does not accept x. These two things are equivalent. So when I get an answer from you about whether this machine accepts the empty set or not, then I've got an answer to my original question. If you say it accepts the empty set and that's nothing, then I know my original machine doesn't accept x. And if you tell me it accepts something, then I know my original machine accepts specifically x. And that's the answer, yes. So if you got a way to do this, I can do this. And I got no way to do this, so you didn't have any way to do this either. All right, questions about this? We're going to do one more trick like this. That might not be quite as tricky. It'll take a little bit more of an effort to come up with the transformation. And then you'll see that there's really something very similar between all these tricks. They're all really much the same, and that's where Rice's theorem comes from. And I'll just tell you what that theorem is before we're done. And then we'll shift over to some other kinds of reductions. All right, questions? All right, so before I do the next one, let me do something maybe a little bit simpler in between. We know now that, that there's no way to determine whether a given Turing machine accepts absolutely nothing. What if I ask you this question? Does a given Turing machine M accept a given regular set R? Question mark. So I give you two things now, a finite state machine and a Turing machine. And I'm wondering whether they happen to be the same language, whether this Turing machine accepts exactly the things that this particular finite state machine accepts. Right? If I give you two finite state machines and I'm wondering if they do the same thing, then the answer is, yeah, you can figure it out. You can minimize them, compare them. But if I give you a Turing machine and a finite state machine, maybe there's no way to know whether they do the same thing. Well, what if there was a way to know? What if you had a way to determine, given a finite state machine and a Turing machine, that they actually accepted the same language? What could you do if you had that method? Well, you could do this. You could solve this problem. How would you solve this problem if you could solve this problem? How could you figure out whether a given Turing machine accepted absolutely nothing if you could figure out whether a given Turing machine could accept any specific regular set? Right, the empty set is a regular set. You just give a finite state machine that doesn't accept anything. And you hand that finite state machine over to here, and you let this person who can tell whether Turing machines accept particular regular sets tell you whether it's the same or not. And if you give this person a specific regular set, it'll work the same way. So this person checks whether M actually accepts the empty set, and that's just what you want to figure out here. So this is just a more general problem than this. And if this one's hard, then certainly the more general problem is hard. This is a reduction where all you do is say, let R equal the empty set. That's the whole reduction. You don't do anything else. You don't change M. You let M stay the same, and you let R equal something specific. It's a reduction by restriction. You're saying basically that the harder problem is just a special case of this problem that you're wondering about. So this kind of reduction comes up a lot, and it can be bewildering. You stare at it, you think, oh, gee, I don't know. How do you show that's undecidable? But really, it's kind of obviously undecidable because it's just harder than this because it's a generalization of this. If you can do this one, you can do that one because it just means you put in a particular value for R.
How do we know when we're trying to, if we were trying to do this reduction ourselves, how would we know that we could set R? I mean, it seems like R is something that someone else sets, that we have to do it for any general R.
That's right. That's right. You do have to do it for any general R. So we're going to assume somebody's got it done for some general R. right? Let's assume somebody's figured this out. I'm going to convince you that they're lying. Somebody's figured this out for some general R. They know how to do it no matter what R you give them. That's to your advantage, this objection you just brought up. Anybody can do this for any R, for any M. You guys know how. And I want to solve this problem. I want to solve the problem where I'm given a machine and I want to know if it's empty or not. So I just give you my machine, and I give you a finite state machine that happens to equal the empty set. And you can do this. So you can certainly do it for my particular finite state machine that equals the empty set. So that generalization is to my advantage as the prover to show you that this is hard. I want to solve a problem that's much easier than this. That's for a specific machine. So if I know that problem's hard already, then certainly this problem's hard also. I'm convincing you this problem is hard specifically because it's more general than another problem, which I already know is hard.
But if we were to reduce the other way, then...
There's no obvious direction to reduce this to this.
Okay.
No, definitely not. No, you don't reduce from general cases to special cases. You reduce from special cases to general cases. Because reductions are, remember, this symbol. So you're basically saying that this is easier than that. I'm saying that this is easier than that. So if that's undecidable, then so is that undecidable. Does that make sense, Doug? It's a good question. Are there other questions about this restriction reduction? Chris, okay? You're nodding deeply. Okay. Let's switch this question. Does a given Turing machine accept a given regular set? What if I don't want to ask a question that's quite so general? So I want to make it, maybe something that has a chance of being decidable. This doesn't have any chance. Because if I could do this, I can do this. What about this question? Does a given Turing machine accept a language which is regular? I'm not giving it a particular set to check against. I'm just asking whether the language it actually generates is equal to some regular set. I don't know which one it's supposed to be, but is it one of the infinite number of regular sets? Could it be one of them? Maybe that's something we can do. Being able to solve this problem doesn't let us solve this problem. If I give this machine over to this person who has this solution, and they say, sure, the machine you gave me accepts some regular set. I have no idea what that regular set is. And I have no idea whether my machine accepts empty or not. So this is a different question altogether. This isn't a question of I give you a Turing machine and a regular set, and are they the same? I'm just giving you a Turing machine, and I want to know, does it accept some regular set? Is its language regular? Well, yeah.
Is this the same as saying you could reduce a Turing machine to a finite state machine?
Yes. Here's a Turing machine. Is there a way to turn it into a finite state machine? That's another way of thinking about it. Sure. Is there some way to make this Turing machine into a finite state machine where you stop using the tape? Is it the same as some language that is a finite state machine? Sure, it's the same way to look at it. So this problem is also undecidable, but it's not an obvious restriction reduction. It's going to be a similar reduction to what we did at the beginning of the class, and it's going to come from here. And it's going to be the same kind of trick that Peter didn't like before, but maybe this time we'll be more used to it, so it won't seem so objectionable. The m and the x, we're going to have to convert it to another machine. And here's what we're hoping. We're hoping that the solution to this question will give us a solution to this question. So that if somebody could decide this, then they help us decide the halting problem. And we know the halting problem is not decidable, so then we know that this is not decidable. So let's think of a way to take our general machine and a given input, change it into a different program, so that if that new program happens to be the same as a finite state machine, then the original machine you were given accepts the original string that you were given. If and only if. Let's make a new machine so that the answer to this question about it being a regular set tells you the answer to the original question about whether a machine accepts a given string. We'll call this, I don't know. We'll call it MP for Peter. That doesn't mean you have to come up with it. You just have to be skeptical. All right. So what's MP going to look like? Let's try some things, whether they work or not, and see what works. If we pick something that doesn't work, we'll find something that does work pretty quickly. Here's my method whenever I don't really understand what's going on. I pick the last thing we did and I try that. And I figure out why it doesn't work. And then I fix it. So Michael did the last thing. Let's try the same thing Michael did last time. Michael said last time, let's chuck this if statement in front. So if the input is x, we'll actually run the machine on x. And if the input isn't x, we just reject everything. Right? Let's assume we just do the same thing. Because if we see why that doesn't work, maybe we'll get a sense of how to fix it. All right, let's do the same thing. Let's do the same trick. If the input's x, we run the machine on x. Otherwise, we reject the string no matter what the input is to this machine. This is a machine that takes input. We're going to compare its input to x. If it's the same, we'll run it. If it's not the same, we reject. Now, let's see what happens with that machine if we send it to this program. If this program says the language is regular, what do you know about this machine MP? Remember, MP, the way Michael gave it to us, accepts either the single string x or it accepts absolutely nothing. Right? So if this thing says the machine accepts something regular, then what do you know? Do you know anything about whether you can distinguish between accepting x and the empty set? Those are the two possibilities for this machine. It either accepts a single string x or it accepts the empty set. If I give this machine to somebody, they say, hey, I know that this machine accepts a regular set. Do you know whether it's a single string it accepts or it's the empty set? You don't know because both those things are regular sets. Right? So knowing that the language of this machine is regular doesn't help you distinguish between whether it's x or empty. Knowing whether it's empty helps you distinguish between whether it's x or empty. But knowing whether it's regular doesn't help you distinguish. What if they tell you that it's not regular? Will they ever tell you it's not regular? It's going to guarantee to be a single string or the empty set. So actually, it's kind of a silly thing to give this person because you know what they're going to tell you. They're always going to tell you that the answer is regular. Not only won't you learn anything from their answer, but you can predict their answer before you give it to them. That is like a surefire, waving the red flags. Don't use this reduction. You want to get a lot out of this person. You are milking this person for everything. You're milking them for an undecidable problem. You're getting everything from them to solve this undecidable problem. If you can actually predict their answer, then you haven't done very much in this reduction. You've really done something good in the reduction if when you send it to this person you have no idea what the answer is at all, but when you get the answer, then it helps you go back here and get the correct answer. So it's a good hint in a reduction that if you have any idea what the answer is after your reduction's done and you give it to that person with a solution, it's a bad reduction. So we've got to fix this reduction. We've got to fix it in such a way that the choices between the things that it might accept don't end up being either a single string or the empty set. But what should the choices be? Either something that's a regular set or something that isn't a regular set. Let's fiddle with this machine so that we know that when it's all done, accepting all its strings and doing what it does, that either it accepts a regular set or a non-regular set. And let's have that somehow depend on whether the original machine accepts x or not. So what can we try to do? We can still look at the input x and that came from here and decide what this machine should do, but we have to do something different than what Michael said before. Chris, do you have an idea? You thinking of something?
Convert it to something like that plus reverse. I'm still confused.
Oh, so Chris is trying to think of something that's definitely not a regular set. Why don't we think of something simpler that's not a regular set? What's the first thing you can think of that's not a regular set? 0 and 1n is like a classic not regular set. So let's make this machine accept 0 to the n 1n whenever m, say, doesn't accept x. How do we do that? Is there any way to do that? Think about this for a minute. Take 2 minutes to think about it. If you think about it, you had a better chance of getting it after I write it on the board. I'm trying to avoid this feeling of, oh, that's a magic trick, and and I see it, but I don't get it. So just think about it for a minute. Does anybody have a suggestion? What can we try to do? This machine is going to depend on m. You got this big complicated machine, you don't know what it does, and you're going to add a little bit in front of it for this machine. So let's try something and see if it works. Then we'll fix it if it doesn't, like we did before. What we tried before definitely didn't work, and we have an idea of where to go from there. What we tried before was either this machine will accept a single string or it'll accept empty, and both of those things are regular, so that was a bad set of choices. Let's make it so that this machine sometimes accepts a regular set and sometimes doesn't accept a regular set. So here's what we'll do. Okay, if the input is of the form 0 to the n, 1 to the n. So you look at the input, and you look at it. And if it's 0 to the n, 1 to the n, if it's in that form, then you accept the string. Okay? Then accept. I like that because at least now I'm getting a non-regular set for some cases. Now if the input's not of the form 0 to the n, 1 to the n, what if it's...
If x is...
Not if x. This is a machine that takes its own input. Whatever the input to its tape is, if it's 0 to the n, 1 to the n, we'll accept it. So this machine is going to accept 0 to the n, 1 to the n. We'll see if this works or not, but at least it's a start. Now what if the input's not 0 to the n, 1 to the n? Then if it's not, otherwise, else what? Else, let's run m on x. Just take this machine that I had before and run it on this input string. Let's try this and see how far off it is if it's off. Run m on x, and if it accepts, then accept. Then say yes. So just simulate m on x. How far off is this, or does it work? What goes on here? Here's a new machine. I'm going to give you this machine, and I'm going to ask you, does it generate a regular set? Does it always generate a regular set? Does it always not generate a regular set? How far are we off here? What kind of languages does this machine accept or not accept? Does it always accept 0 to the n, 1 to the n?
Yep.
It always does, right? What about all the other strings? What else does it accept? It accepts 0 to the n, 1 to the n, and as far as all the other strings go, it might accept x, right? So either it accepts 0 to the n, 1 to the n, or it accepts 0 to the n, 1 to the n, union with x. Everyone agree? No. Maybe. You're not sure. Let's make sure you understand what the machine's supposed to do. The machine's supposed to do nothing but go ahead and look at its input, and if the input's in this form, it's supposed to accept the input. So it always accepts those strings, 0 to the n, 1 to the n. If it's not one of those strings, then it doesn't do anything special. It just goes ahead and runs the original machine it was given on the input of that machine. It doesn't even look at its input. So if you get something of the form 001, it doesn't look at that or reject it. It just goes ahead and runs m on x. And if m on x accepts, then what does it accept? Then it accepts the original input that was given to it. Let me do some examples. There's too many confused faces.
M, so that's supposed to be doing again?
there's no M sub.
The machine that we feed it.
We have no idea. You mean this machine?
Yeah.
That's just some general machine that's given to you, and this is an input on that machine. And I've changed it now to this machine. Let's make sure everybody knows what this machine does. This machine, MP, has an input. If I give it 0, 0, 1, 1, what does it say? It says accept, right? Check. If I give it 0, 1, what does it say? Accept. Now, this machine is based on, right now I'm showing you how it works without telling you what M and X were, but it is based on M and X in some ways. You just haven't seen that yet. Say I give it something that looks like this. Does it accept this or not? It depends, right? What's it going to do to decide whether to accept this or not? It's going to run the original machine on the input given, on this X, which has nothing to do with the input 0, 1, 0, 1, 0. Just whatever this X is, it's going to run M on X. And if it ever accepts X, this original machine, then this machine is going to put a check here. Everyone understand? All right, so let's go through the possibilities. Let's say M happens to accept X. Then is there going to be a check here? Is there going to be a check here? It's going to be a check here. There's going to be a check on every single string, because if the string is not of the form 0 to the n, 1 to the n, all this machine does is run the original machine you were given on X, and if there's an accepting computation, it goes ahead and says yes, 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 yes. So what are the possibilities for this machine MP? What are the two languages that it might accept? If M accepts X, then what is MP accept? It accepts everything. And if M doesn't accept X, what does it accept then? 0 to the n, 1 to the n. Because it puts x's on all these if M doesn't accept X.
I still don't see how it accepts everything.
Because all it does to decide, say it's given 0, 1, 0, 1. Let's go through its program.
Okay.
0, 1, 0, 1 is not of this form.
Right.
So it doesn't accept. Now it goes on to this stage, and it runs the original machine on the original input.
Oh, it runs the machine on X, not...
Not on itself. It runs right. Right. This is my machine with my X, the one that I'm trying to figure out whether this machine accepts this X.
Uh-huh.
This is how I fixed it to MP. And now I give it to you, and I tell you to give me the answer of whether this is regular or not.
The string you run through it, it checks if it's the form of the n, 1 of the n, and if not, then it runs X, which it accepts. So
Not which it accepts. We don't have any idea whether M accepts this X or not. But if M accepts this X, then we go ahead and accept whatever string was given to us.
The 0 to the n, 1 to the n, is that X?
No.
No.
The thing that is compared to 0?
No. I see. There's some confusion here about the input. You're given a Turing machine and an input here to figure out whether this machine accepts this input. We are converting this to another machine, which has its own input. This is a program and an input that you're given. You're wondering whether this program accepts this input. I'm converting it to another program, which takes its own input completely separate. You already get this. And that input goes in here, and I'm telling you what to do with that input. If that input happens to be of the form 0 to the n, 1 to the n, then I accept it. And if it's not of the form 0 to the n, 1 to the n, then I ignore it completely, and I run the original machine I was given on X, whatever X was. So I'll put a little comment here. Ignore my own input, and instead run M on X. Right? So look what we've done. We've made a dichotomy here. We've taken MP and had its language output be two possible things. One is everything, if M accepts X, and one is 0 to the n, 1 to the n, if M doesn't accept X. And I built it just for that purpose. So now I give this MP to you. And you know how to check whether machines happen to be the same as some kind of finite state machine. you know a way to do that. And I give you MP, and you tell me, hey, that's not the same as any finite state machine. And I say, it's not, thanks. Which one of these possibilities can I rule out? Well, if it's not the same as any finite state machine, it's certainly not sigma star. It's got to be this one. And if it's got to be this one, then I know M doesn't accept X. So I got the answer to my original question. And if you tell me it is a finite state machine, I know the only way that could be is if it accepts sigma star, and then I know M does accept X. So it's a sneaky way for me to get the answer to the question whether M accepts X by using you, somebody who knows a way to check whether a machine accepts a regular set or not. That MP can only accept either everything or a particular set that we happen to know is not regular. So when I get an answer as to whether this machine has a language which is regular or not, I know exactly which one of these cases occurred. If we use Michael's reduction just blindly, then these two cases would have been the empty set and a single string, both of which were regular. And then knowing whether the language is regular doesn't help me distinguish between this one or this one. And that would be bad. All right, questions about this?
Can you explain that last step about sending it to the final step out?
Yeah, let me go through it again. I'm trying to figure out a way to decide whether a given machine accepts a given string. I know there's no way to do that, but I'm going to convince you that if there was a way to do that, I'm going to convince you that if there was a way to solve this other problem, then there would be a way for me to decide whether M accepts X. And I'm going through that logic now, this convincing of linking one problem to the other. So the other problem, this problem that we're interested in is somebody gives you a machine and asks you whether it is the same as some finite state machine. And let's assume that you've got a way to decide that, whether a given machine is the same as some finite state machine. I am now going to describe to you this way of me being able to decide if a given machine accepts X. So somebody gives me a machine, somebody gives me X, and I have to figure out whether the machine accepts X. So here's what I do. I take that machine and I take X, and I construct this new machine called MP. And I'm going to give this machine to you and ask you to tell me whether it's regular or not as far as its language goes. You presumably have some way to do that. If you tell me the answer that it is regular, through my logic, I am going to know that my MP accepts everything, and therefore M accepts X. And if you tell me that it's not regular, through my logic, I'll know that MP accepts this set, and therefore M does not accept X. And that logic is all built into how I created MP. What MP does is look at its input. If it's 0 to the n, 1 to the n, it accepts it. But otherwise, it runs M on X, the original, and if that gets accepted, it accepts everything. Otherwise, it accepts nothing else and just gives me 0 to the n, 1 to the n. Does that give a bigger picture?
Yes.
Chris?
I think I lost track of how determining whether or not a string is accepted by a machine is undecidable. Isn't that just what a universal Turing machine does?
A universal Turing machine does that, and that's why this problem is recursively enumerable. But a universal Turing machine does not decide that problem. It doesn't make it decidable. It answers the answer yes when the answer is yes. It always does that correctly, but it doesn't give it the answer no. We proved this was undecidable yesterday by diagonalization, specifically showing that there is no way in general to give the answer no correctly.
That's the halting.
Right, that's the halting problem, right. That's what this is. So now we're taking that halting problem and shifting it and showing that all these other problems are also hard, because solving any of them would solve this halting problem. All right, questions about this? All right, let's do a very quick generalization of this to a different problem. What if I asked you, maybe I can't figure out whether a Turing machine is the same as a finite state machine. Is it the same as some given context-free language? Fix this reduction so that it works for that problem. This is an easy switch, an easy generalization. Here's what I do. I go over to this MP, and instead of using 0 to the n, 1 to the n, I use something that's specifically a context-free language. Right now, if I use this reduction as I stand, and I give it to you, and you tell me this is a context-free language, you're always going to tell me it's a context-free language. Either I get sigma star or I get 0 to the n, 1 to the n. And if I give it to a context-free language checker, you guys are always going to say yes. I'll learn nothing. I won't be able to distinguish this from this. But if I fix this reduction so that it looks like this, now if I give that MP to a context-free language checker, and it tells me yes, I know it's got to be sigma star, because that's not context-free. And if it tells me no, then I know it's got to be this, because that's the only non-context-free option. So the question of whether a Turing machine is the same as a context-free language is not possible. Now that's a really important question. You come up with a new programming language. You wrote it out in a grammar. Somebody writes a program that accepts all the strings generated by that grammar. They write a compiler based on that grammar. You want to know whether they followed your grammar correctly. Did they go ahead and do what you said the grammar was supposed to do? You got a program, you got a grammar. Do they do the same thing? Undecidable. Right? So that's a real problem that you'd like to be able to do, and there's a proof that you can't do it. The thing about these proofs is that they're all magic. I can fiddle with this stuff so easily. Anytime there's a question about a Turing machine language that's something, that I have one example of a language that's not context-free. And here's what Rice's theorem says, and then I'll stop this stuff and go on to something a little less abstract. Rice's theorem says this. Let's say you have a general problem like this. You're given an M, and you want to know something about the language of M. Is the language of M something? Quotes. Is it regular? Is it context-free? Is it empty? Is it everything? Rice's theorem says that if you want to ask a question like this, give me all the Turing machines such that their languages have something special about them, as long as that something special is not completely trivial, then this problem is undecidable. And his proof is what we just did. If you can imagine what we just did done more abstractly, he does what we did completely generally for any something in those quotes. Where it's regular or context-free or empty or a singleton, he just shows how to do this reduction no matter what it is. As long as one condition is true, that there's at least one Turing machine that has this something true about it and one that doesn't. If they all have something true about them, then that's trivial. And the answer is just always yes or no. But as long as there's one Turing machine that has it and one that doesn't, he can go through this grammar. He can go through this proof. Where does he use that condition that at least one has it and one doesn't? It's to be able to get this. It's to be able to get something that he knows doesn't have that property. What's an example of something that is trivial? Here's something that's trivial. Give me all the Turing machines, and I'm going to ask you, is the language that they generate recursively enumerable? Well, by definition, it's recursively enumerable. Whatever they accept is recursively enumerable. There's a Turing machine that does it. The answer to that's always yes. So his theorem doesn't apply to trivial things. But anything else interesting you want to know, is the language that M generates equal to everything? Undecidable. Equal to nothing? Undecidable. Equal to a regular set? Undecidable. Equal to some context-free language? Undecidable. Anything interesting you want to ask about a Turing machine that relates to its language is undecidable. That's Rice's theorem.
Troy, what about something like, does a Turing machine have an accept state?
That's a good question. That particular question doesn't relate to the language of the Turing machine. These are questions that all relate to the language the Turing machine generates, not to the particular Turing machine you're using. So if you want to ask a question about Turing machines that relate just to the machines themselves rather than the languages they generate, this says nothing about that kind of stuff. And there may be plenty of decidable problems that just say, does this Turing machine say have 2 or more states? Does this Turing machine have a final state? That's a question about the machine and not the language that the machine generates. So Rice's theorem really has 2 conditions. One is that it's not trivial, and the second is that it's a question about the language, not about the machine itself. Obviously, you could have lots of different Turing machines that generate the same language, and you could ask special questions about it. That's a very good question. Yeah. Yeah.
You meant, Michael, it has an accept state whether or not you can get there, right?
Yeah, yeah.
Right.
You meant just, let's check if there's an accept state. Right. You're not trying to ask, does it accept something?
Right.
Because that is harder.
Right.
Right. Just looking for an accept state doesn't tell you whether it accepts something or not. Because it might not ever be able to get there. Okay, questions about this? All right. I'm going to let this topic go. You should keep in mind then that everything you really want to know about Turing machines is undecidable. And we'll move on to a different topic. We're going to think about a problem now and wonder about whether it's decidable or not. And this is a fundamental distinction from the things we've been doing. The problem that we're going to talk about now is going to have a different result. And at the heart of it is going to be an implication that there's a hierarchy of problems that take a different amount of time and space. And here's kind of the picture we're going to be dealing with. The normal decidable circle now is going to get refined into lots of other circles. We're going to move away from computability theory, which talks about what you can compute, down to complexity theory, which talks about how much does it cost us to compute it, assuming you can already compute it. So everything in our circle now is in the decidable circle. And the question is, how much time does it take? So we'll start with a very, very simple picture to start, P and NP. Polynomial time algorithms and non-deterministic polynomial time algorithms. And this is going to get refined and refined. We're going to have about 5 or 6 concentric circles in here by the time we're done. This represents time complexity. There's also space complexity. And we need to define what those things mean in terms of a Turing machine. So, let's do that. Here's a Turing machine, M, and here's the tape that it looks at. It's got its finite states in here, and it looks and goes left and right. And now that we've got Turing machines and we know what decidable is, let's define what we mean by time and space requirements. It's kind of intuitive. So let's say this machine takes some input. Let's say this machine is supposed to accept 0 to the n, 1 to the n. So it takes some input. It's supposed to accept things of this form. And it goes back and forth, and it does some checks, and sooner or later it ends up saying yes, or it stops and says no. Always stops. This is a recursive, decidable problem. No infinite loops here. It's always going to say yes or no. Guaranteed. Okay. How would you measure the time that it takes to do this? What would you think is a good measurement of time? One that somehow has a correlation to the time we think of as on a computer, which is, 1 step each for each line in the machine code. What's a good analog for time on a Turing machine? Okay, what about moves on the tape, or just moving over arrows? Every time you move over an arrow, you move to the left or to the right. Count how many times you moved over arrows. That's the amount of time it takes to accept or reject a string. For a whole language, the time it takes to accept or reject is the maximum of all those. So let's say I can convince you that to accept or reject this language, we never actually use more than n squared steps. I'll even give you a method. You see a 0, you scan over all the zeros until you see a 1, and then you X them both off. Then you go back. How long does that take? It takes n to scoot over, then you go back. N to scoot over, you go back. N to scoot over, you go back. You do it n times, so it's about n squared steps. So there's an n squared Turing machine algorithm to accept this. Now the thing is, just like your own problems or your own programming languages, we don't really care about constant factors when we're talking about time complexity. But what's different about Turing machines is I have a one-tape algorithm I just described to you that takes n squared to do this. If I added an extra tape, I could do it faster. I could do it in n. How could I do it in n if I added an extra tape? What could I do to speed it up? I got another tape to help me. Neil, you got an idea? Stagger the heads and read across. So one machine would just stay at the beginning. The other machine, I guess we copy the input to the other machine. That only takes n to copy input. And then we'd start the second machine at the 1, and then read the zeros and the ones together. And if we hit the blank at the second tape, the same time we hit a 1 on the first tape, then we stop. It's a perfectly reasonable idea. That takes linear time. So we just cut down our n squared to linear. That's not a constant factor. That's a serious improvement. You should keep in mind that depending on the version of the Turing machine you use, even though it has the same power, using a different version with different tapes does change where a problem lies as far as its time complexity. And people do a lot of work on this. They do a lot of work with how much you have to pay in order to give you 2 tapes. Can you always do it with a square explosion in the time? Or are there versions where it takes, more than a square? Here's a version, where we added a second tape and we knocked it down by a square root, where there was a square blow up by getting rid of that tape. So there's all sorts of theorems about this. We won't get into too many of them, but you should know that there's a trade-off between the model and how much time it takes to run something.
This theory of computation doesn't concern itself with the time to write the code.
No. That's software engineering. Right. It's being a CEO. Or maybe a CTO. No, it doesn't. Yeah. No, I guess you just assume somebody can write them. Okay, so keep this in mind, that the model changes the time complexity. What would space complexity be? How would you measure space? We measure space by the memory. So what's the analog to the memory? So the analog to time is the number of movements. What's the analog to space? Length of the input is the size of the input, but that's not necessarily all the space we're going to use.
How many symbols you care about?
Well, the tape's infinite, or how many symbols you care about on the tape. How about how many symbols we actually visit on the tape? You can visit one more than once. That won't count more than once. That's time. But how about actually the total number of symbols we actually ever look at? So if we only look at, between here and here, then we'd say this algorithm takes space, equivalent to whatever that number is. How much space does it take to accept this set, assuming there's one tape? Something proportional to n, not n squared. There are plenty of other examples where you might use extra space, where you might have to write stuff over there on the side and use memory. Yeah?
There are also situations where stuff that's important back here you forget about later. And you could go back and overwrite it, but that would be a time complexity problem. And so you just leave it there and move on to other parts of the tape.
So a trade-off between how much time you're using and how much space you're going to need. Like if I wanted you to be specifically restricted to a particular amount of space, you might be able to make up for it a little bit with extra time. Yeah, and there are complexity trade-offs between simultaneous time and space and things like that. Absolutely. All right, so now that we understand space and time, I want to refine this picture a little more and see if we can get a beginning, kind of an overview of what complexity theory looks like, and try to explain why these classes are one inside the other relative to this definition of time and space, and how you can do one machine in terms of another machine by simulating it and keeping track of how much time or space it takes us to do it. So, here we go. Here's P. Here's MP. Now, what about, this is just time classes. Certainly NP includes P because it's everything you can do in P plus non-determinism. We have no idea whether this is a proper enclosure. That's the big open question in theoretical computer science. These two might be the same. We don't know. What about the next stage? I'm going to write something out here called polynomial space. That means you use a polynomial amount of space on the tape. That means just a polynomial number of symbols, not a polynomial number of steps. Why does this include this? Why is this out here? Why does polynomial space include polynomial time? Why is anything that takes polynomial time definitely take polynomial space, but why there are some things in polynomial space that might not take polynomial time. Why are these harder problems, intuitively or rigorously? Explain that.
It takes at least one step to generate a symbol on the tape. So.
Okay, so something that takes, say, uses 30 symbols on the tape has certainly have to use at least 30 steps, because to get to every cell requires a step. It's possible, if you're only using 30 steps, to reuse them many, 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 many times and use lots and lots of time. How much time? If you have 30 cells, how much time? Seems infinite, seems unbounded. Well, we'll talk about that in a minute. But certainly, if you have something that uses only 30 steps, it's got to use at least 30 symbols. If you have something that uses 30 symbols, it might use a lot more than 30 steps. Questions about that? So that implies this relationship. The fact that NP is in between these two, that's still a mystery, and we'll be going through that at a different time. But it really is. It turns out that polynomial space is enough to do non-deterministic polynomial time, that it really is in this order. Nobody has any idea whether these things are properly enclosed. Nobody knows whether these two are different or not. For all we know, there are things in polynomial space, and every one of them can be done in polynomial time. Now, you know there are things in here that are called NP complete, so that if they ended up in here, the whole NP would end up in here. There are things called P-space complete. Problems out here that if they ever ended up in here, all of P-space would end up in here. And we have those problems because we have no way to distinguish between these two classes in any other way. We don't know if they're really different or not. But intuitively, these things are harder than these things, and these things are harder than these things. What kind of problems end up here? Problems end up in here that are P-space complete, which you can't even figure out a way to do in non-deterministic polynomial time. There are problems which it seems like you can do almost everything in non-deterministic polynomial time. I mean, you get everything for free. 3 satisfiability, just guess the satisfiable formula, that's for free, and then check it in polynomial time. What can't you do in non-deterministic polynomial time? What might be stuck outside in this never-never land of P-space? Well, there's a whole host of problems that are all similar. And I'll give you like a classic example. It's basically any two-person game. And there's a really, really famous one that you've played when you were children, or probably did. And it can be described on a graph, but I'll just describe it to you like you played it when you were children. And then I'll talk about what this problem really is, and try to give you a sense that it's not able to be done easily in non-deterministic polynomial time. And as far as anybody knows, there's no way to do it here, but nobody's been able to really prove that there's no way. Here's the game. You and your friends sit there, and you come up with geographical locations, and you take turns. So I start with New York, and then Chris has to come up with a geographical location that starts with a K. Kathmandu. Most people say Kentucky. Kathmandu. So I say Uruguay. Your turn, Chris Walker.
Yemen.
Yemen. I'm stuck. All right. So you play this game until somebody gets stuck. Now, in the car, this is just a game, make sure the kids don't drive the parents completely batty on long car trips. And it's usually a game to see who knows the most places, or who can just make them up in a clever way. Right? So I would just stick north and south prefixes to many places, whether they have them or not, and you can go a long way with N's and S's. In any case, especially if you live in New Jersey, because anyway.
So you cheat your kids.
I don't cheat anymore. I used to cheat when I was a kid. The real way to play this game is that everybody gets a book with all the places in them. So it's not a question of who knows more places. The real way to play this game is everybody's got the book. And when it's your turn, just go ahead and look up something that starts with that letter and yell it. And then everybody's got to cross it out. You can't use the same thing more than once. Everyone understand? That's the real way to play the game. And the question is, given a book of names, who wins the game? The person who goes first or the person who goes second? Everyone understand the question?
That's the real way of playing.
That's the way to define the game for real. I guess it's the completely unreal way to play. So here's what it looks like. It looks like a directed graph. If this is Kentucky, then there would be an arrow to Yemen. Okay, there would also be an arrow to Ypsilanti, yes. And there would be an arrow from Ypsilanti to Indiana. So you just make a directed graph. And you play a game on this directed graph. We take turns. I start anywhere I want, and I X out the thing I started. Now you can move to anywhere that the arrow points to, and you X out what you want. The first person to reach a dead end loses. This is a graph problem. It's not really a problem about remembering names. It's just a problem on a graph. And it's a really simple problem. Okay, you just move it along, and the first person that you can get into a dead end loses. And you're wondering who wins that game.
Your graph, though, would have repeated names in it that would all have to be crossed out.
No, because once you cross the no. Every geographic location has one node.
There's all sorts of words that end in the same letter, so couldn't the next one after that, after any of those?
So like if this is Kentucky, and this is Yemen, and this is Ypsilanti, and this is Indiana.
Okay.
You might go back here. There might be lots of ones that end in K.
Right. That's right.
But if you're at this and the only place back is to X values, then you lose. Nobody knows any way to solve this problem with a non-deterministic polynomial time algorithm. Let's try. How would you solve this with a non-deterministic polynomial time algorithm? You got polynomial time on your side, and you can guess to your heart's content for free, as long as you combine them with ORs. Well, here's one way. What if I just guess a sequence of moves that end up with me winning, the first person winning? I go here, I guess my opponent goes here, I guess I go here, I guess I go here, and I check, and I find out that that sequence of moves is a win for me. Does that mean I've convinced you that I win the game?
That's assuming you know the moves that your opponent's going to take.
Right. And my moves, it's okay, because my moves I can combine with ORs. You know, either I do this, or I do this, or I do this, and I can check all those ORs in parallel for free with non-determinism. But every other move is my opponent. And I don't win just if he moves here, or he moves here, or he moves here, or he moves here. I have to check the and conjunction of all those things. I have to check whether my opponent moves here, and he moves here, and he moves here. No matter which way he moves, there's got to be a way for me to continue. It's there exists a move for me, such that for all moves for my opponent, there exists a move for me, such that for all moves for my opponent. It's a alternating quantifying from there exists to for all, just like you did with the minimax that we did in the algorithms course. And the only way to really check this is to check a whole tree that looks like this. I guess my move, and then I got to check all my opponent's move. For each of those, I guess my move. I can cut off the branches when it's my turn, but when it's my opponent's turn, I got to actually try the branches. So the non-determinism helps me cut off branches when it's my turn, but doesn't help me cut off branches when it's my opponent's turn. So I get a big fat tree that expands exponentially. If there's n values in this game, then there's going to be 2 to the n things in this tree, and I don't get polynomial time. So non-determinism and polynomial time isn't enough to do this. How do you do it in polynomial space? There should be a way to do it in polynomial space. Doesn't matter how much time you take, as long as you have polynomial space.
Worst case, there are n nodes.
No, there could be 2 to the n nodes in the tree.
Well, no, for the number of cities.
Right. There's n cities. Sure.
In worst case, each city connects to all the other cities.
Sure.
So
how do I go ahead and check this big tree of possibilities without storing more than just that many cities? Basically, what I want to do is kind of do a traversal through this tree, doing an and/or connectivity without ever storing the whole tree. Storing the whole tree is too big.
But you can do, but each time you try it, you can do it on this.
It's basically doing one of these depth first searches and sending the information back in pieces, so that the only thing I actually store in my machine is the length of one path at any time. And then I back up, and I go down another path. And I back up, and I go down another path. The time I'm taking is horrible. It's this whole huge exponential tree. But the space I'm using at any time is just the length from the root down to the bottom. And that's polynomial time. That's n time. So I can do this problem, I can figure it out in polynomial space, but I can't figure it out in non-deterministic polynomial time. And all the p-space complete problems are just like this. They're all alternating games. I'll give you an alternating game on 3 satisfiability. This game is p-space complete. I give you a formula, and instead of me asking, is there some way to make the formula true? Is there some assignment, true or false? Instead of that, now we play a game, me against Doug. We got, here are the variables, x, y, z, w, u, v. And down here is a big formula, big long formula. And now I'm not asking, is there a way to make true and false values there to make this formula true? I'm asking to play this game. Doug gets to pick the true-false value for x. I get to pick the one for y. He picks one for z. I pick one for w. He picks one for u. I pick one for v. We go back and forth picking true-false values. My goal is to make this thing true. His goal is to make the thing false. Who wins? Does there end up being a true value for this formula, or does it end up being a false value? Assuming we play the best possible game, who wins this game? So that's called quantified Boolean formula, or QBF. It's just like 3-set, except you alternate choosing the value of the true-false values for the variables, so that you can't just go ahead and pick a collection and check whether it works. You have to alternate your quantifier so that every other one is a for all, and you lose the non-deterministic advantage. 3-set is like this game where everything's there exists. There's some value, there's some value, there's some value. You pick the true-false value, you get it all for free. There exists is like non-determinism. For all kills non-determinism. Non-determinism is great with ors. It's terrible with ands. You can't use it at all to do ands. And now we have to do it with ands. I pick it, that's an or. Doug picks it, that's an and. For every way, whether he goes true or false, I got to win. So this problem is harder than 3-set. As far as anybody knows, it sits up here. The same way satisfiability was the first NP complete problem, quantified Boolean formula is the first p-space complete problem. All right, so this is give you a sense of what time complexity and complexity theory is kind of all about. I want to just quit with one little thing to give you a sense of something that I worked on, I don't know, maybe it's 6 or 7 years ago already. But it's the same geography game. Because this geography game was proved by, it might have been proved by Mike Sipser to be p-space complete. But there's a variation in this geography game that I once gave as a programming assignment to some freshmen. And then I thought about it and wondered whether it was easy or hard. And then it ended up being 2 or 3 years later writing a paper on it. Well, they could program it. They just couldn't program it efficiently. Here's the game. You play geography again. You have the same book. You give everybody a book. You play the game. But this time, instead of having to take your move from where the other person left off, like you start. Cleveland. So I don't have to start with D. I can start with anything I want. I'll start with North Dakota. And now Chris has to continue, and he only has to continue with what he left off last time. And I continue with what I left off last time. So it's like playing with yourself, geography. You just sit in the same room, but every person just keeps going, with their own list. It's nowhere near as much fun, right? And what's your gut instinct about this game? Doesn't it seem like it might be easier? Right? I mean, yeah, it's playing with yourself, geography. I see. It seems like it might be easier because you don't have to worry about what the other person's going to do. They don't seem to be interfering with you as much.
Do they use it up?
They are using it.
Right. You can't use Cleveland. I can't use Cleveland again. Right. So they really do interfere with you, just in a more subtle way. You know what this is like? What reminded me of this after I thought of it, and then I had the students program it. It reminds me of this game that you see in this old Disney movie called Tron, or a video game called Tron, where you have these two people riding these virtual motorcycles, moving around, and they try to cut each other off so somebody crashes first, because there's no more room left. So imagine this game played in a graph. You have the same directed graph, but now you have 2 tokens, 2 places. And every turn, somebody moves 1 spot. I go here. Chris doesn't continue from here. He continues from here. And I go here, and he goes here. And I go here, and he goes here. It's just like Tron. And we try to cut each other off. And the first person who crashes into himself and gets into a dead end loses. It's exactly like Tron, except Tron is real time, and it's really a game of reflexes and not a game of, you could slow it down slow enough so that the person could think a long time on his next move where the best way to go. But it's Tron slowed down a lot. And I thought that this would be an easier game. Or at least there'd be some way to come up with some reasonable strategy. But it turns out this game is piece-based complete also. And the only kind of graphs that you can play this game on that actually have any chance of being understood at all, if you play it on a directed tree, no cycles in the graph, like the book represents just a tree of names, then you can figure out who wins. But if it's any more complicated than that, even if the graph has no cycles in it, so it's a directed acyclic graph, I mean, there are underlying cycles but no directed cycles, it's still hard. So this is one hard problem, even though it seems like it wouldn't be. So that's what we're going to be talking about for the next few days. Complexity theory. Relationships between complexity classes, relationships between space and time, newfangled notions of how to measure complexity, one called an alternating machine that mixes the ands and ors together, and then relationships between them and both results that are practical and results that theorists think are beautiful. Interesting, weird ways of measuring complexity, which turn out, when you give it log n space, to be the same as p space. It's nice to see these things collapsing on themselves and equaling each other, because it makes you feel like your definitions are more robust. So the prettier the theorems, the more robust the definitions, and vice versa. So that's what we'll be talking about from now till the end. There's a lot of things to talk about in these topics, including computations that model probability, interactive proof systems, alternation, all sorts of things. We will visit diagonalization again, because inside P there's going to be a hierarchy. There are things that can be done in n squared that can't be done in n. Things that can be done in n cubed that can't be done in n squared. So we're going to move up and down and try to understand these relationships as best as we can next few days. Okay.